Last time we did some basic integrals, and what that meant is just actually remembering all the derivatives we had already done. So we made a partial list here, and these are the things you're supposed to know immediately. As soon as you see integral of e to the t, for example, boom, it's got to be automatic. That integral is e to the t because it's a basic one. We've already taken the derivative of e to the t, etc., etc., etc. For all these power rules, all the sines and cosines. That's what we did the first time. We said, hey, we got to really get to know all the basic integrals. Check. Then what happened after that? After that, we did the u subs. What exactly does that mean? That means that they were almost basic, except they had some variation of the x in there, and we had to make a substitution u. For example, u is equal to 5x, and we call this a dictionary, and blah blah blah. We turned it into an integral with u's, and that hopefully was easy, and then we were done. That's what we did right after the basic ones. And after that, we did more of the same, but we did it with very trig function intense version of the u sub and the other one, where we use a lot of trig identities. Just remind you real quickly, the flavor of that was something like tangent to the third, and we had to keep exchanging tangent squares for secant squares, sine squares for cosine squares, -1, blah blah blah, or vice versa. That was very trig identity intensive. It's a really nice way to review more of the basic ones and more u subs, and to review your trig identities. That's what we did last time. What we're doing today is slightly different. It's not. It also involves trig functions, but it involves them in a slightly different way. So let's cut to the chase. Let's take the classic tricks of integral, which is exactly this one. You may have seen it before, long time ago when we did derivatives, because we did the derivative of arctangent, and this turned out to be the derivative. So in some sense, it's the basic one. But let's ignore that for now, so we can get on to today's lesson. Today's lesson is about making trig function substitutions. So take this example. Talk is cheap. Let's just get to work. What would happen if I made a little dictionary in the following way? I said, you know what? I'm going to take that x right there, and I'm going to substitute it. X is equal to tangent. I've got to use a different variable, not x. I'll just go with t's, okay? That would put dx equals to secant squared t dt, and this would be my working dictionary. Let's see how it works out. This would be the integral. Let's switch back to white. This would be the integral of 1 over tangent square. I know you're thinking, how in the world would you have thought about that? I know. Just wait a little bit. Tangent squared t plus 1, and then dx. Here's my dx. It can be exchanged for that whole thing. So it's times a secant squared t dt. There's my integral translated in terms of t's. You could use u's or thetas or whatever. That doesn't matter. But here's what happens, and something really nice happens. The tangent, right here, this piece, the tangent square t plus 1, that's actually something famous, right? We've seen that before. Where have we seen that before? It's one of the famous trig identities. It says tangent square theta plus 1 can be exchanged for secant square. And so we go on and we perform the exchange. This one can be exchanged for a secant. Turn it into integral of 1 over secant squared t times a secant squared t dt. And isn't that nice? Look what happens now. This secant squared t cancels with that secant squared t, and all you're left with is, voila. What are you left with? You're left with equals integral of dt. And of course that would be just t plus a constant. Let me write that t better. That would be integral of dt, and that would just be t plus a constant. And that's nice. Now it's customary to revert back to the dictionary and switch back your variables. So tangent t is equal to x. That would mean that t is equal to, that would mean that we could write as t is equal to arc tangent x plus c. That would be one feasible antiderivative function for this one. And so this gives you a different look at the problem we've already done before, with this nice little substitution, x squared plus 1, where we substituted, instead of x, a tangent. Something unthinkable. We've never done this before. We substituted x for some other polynomial version of x, but we never, before this class, substituted x, instead of x, a trig function. That's kind of new, and it's kind of nice. It works out really nicely. But then that doesn't resolve the question, how did we know to make that substitution? How would you have known? Well, that requires a slightly deeper point of view. Let me try my best to shed some light on the mystery of why. How would you know that? I'm going to pause this so I can gather my thoughts. So the secret sauce, the secret to knowing exactly when or how to do this is right here. I'm going to explain to you the secret, the most empowering point of view, I think, for this whole section. And actually this goes beyond this section. This is a huge idea. And it's rarely really explained. Most people just go about doing it, but never really explain it. Let me do my best here. Here's the secret sauce. It's about two big worlds, and they're different worlds. They're totally different worlds. In this world, we've got very ugly things. This is the world of Mondays. This is the world of Mondays. This is the world of mother-in-laws. Everything. This is a Mondayless world. In this world, all days are Fridays. And so it's about making this connection between these two worlds and making a bridge that joins them. Well, I know that sounds crazy. It was meant to sound crazy. Let me explain the two worlds. In this world, you've got things like binomials, things that have two items, 3 plus x raised to the 4th. That's a binomial. In this world over here, you've got a monomial, just one item. Now, how are these two worlds different? Why do we call this the world of Mondays and this one the world of no Mondays? Well, it's because what happens, this one doesn't play nice with others. It doesn't play nice with exponents. If you had to take the 4th exponent on that, you'd have to do 3 to the 4th plus, oh my goodness, you'd have to do Pascal's triangle. That one triangle that goes 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. This is a 1. So it would be 1, 4, 6, 4, 1. It would be 3 to the 4th, 3 to the 3rd, 3 square, 3. It would be x, x square, x to the 3rd, x to the 4th, and it'd be something crazy like that. Anyways, not that elegant. Over here, 3 to the 4th. Oh, this would be 3 to the 4th, x to the 4th. See? You want to get with, you can get with this, or you can get with that. You can get with this, or you can get with that. I told you, they're different worlds. The world of binomials or trinomials, forget about it. How are you going to take that to the 4th? Good luck. I'll race you guys. You guys take that to the 4th, and I'll do this one to the 4th. 5 to the 4th, x to the 4th, y to the 4th. Done. Got enough time to drink my espresso. Cheers. I told you, these binomials, trinomials, they don't play nice with exponents. But it gets worse than that. Monomials play really nice with exponents. But it gets worse than that. They don't play nice with division either. How are you going to divide 125 plus x to the 4th divided by 5 plus x squared? This is a binomial divided by a binomial. You're going to have to do the long division stuff. X squared plus 5, x to the 4th. You're going to have to put placeholders, 125, blah, 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 blah. Later days. Over here, monomial, it's a totally different world. This is this would just be 5. Over that would be 20. 5x squared. Done. You see that? I told you. Monomials, piece of cake. Binomials or trinomials, later days. This is not. They're different worlds, all right? These binomials, they don't play nice with division. They don't play nice with powers. They don't play nice with roots. They don't play nice with anybody. Compared with the monomials, they play nice with a lot of other things. Integrals are no different. Integrating a binomial or a fraction with a binomial on the bottom presents a lot more challenges than integrating one with a monomial. This is a Monday world kind of integral. This is a nice one. No Mondays there. You see, that's so the biggest thing is, hey, over here you've got binomials like 3 plus x squared, and over here you've got monomials like 3x squared. These are the two worlds, separate worlds, and the key to today's lesson, and actually I tell you, this goes way beyond that. The key to today's lesson is to make a bridge, this bridge that will help you cross. Isn't it amazing to think that there would be some sort of bridge, some sort of formula that could help you change crazy stuff like this, binomials into monomials? If that was possible, wouldn't you like to know about it? You would, right? You'd be interested, really interested in knowing about it, right? Well, I'm going to teach you. there are many cases where these binomials or trinomials can in fact be exchanged for a monomial. And when that happens, you can play some music and say yippee-ki-yay. I'm just kidding. Every time that happens, you say yippee-ki-yay, winner, winner, chicken dinner. So that's the two worlds. All right, let me explain more about it. When does that happen? Well, the trig identity, we talked about it just a little bit ago, but the trig identity, this one is full of exchange rates where you can exchange a binomial for a monomial. Think about this one. Whenever you see this one, what you should be thinking, or what you could be thinking is, hey, if I have x squared plus a y squared, I can exchange that for just one thing. I can exchange it for a 1. And I'm sure you've done it many times before. That's an example where a binomial gets exchanged for a monomial. Oh, but wait, there's more. This one right here, here's a totally much more powerful way of looking at this identity. All this time, you probably thought, oh, this is just some Pythagoras identity, whatever. No, today you have a much more powerful way to look at it. What it's doing is exchanging a binomial here for a monomial. And every time you do that, you go from the world of Mondays to the world of Fridays. Okay? That's what you do. So whenever you see this one, you should think, hey, if I have anything that looks like this, a 1 minus an x squared, this is 1 minus blah square, I can make that x a cosine. If I can substitute x equals cosine, boom, I will be able to exchange that whole thing. 1 minus the cosine square, I'll be able to exchange for a sine square. Same thing for this one. You could also do it with sine. If you have a 1 minus x squared, you can make the x equals sine, and you would be in fact be able to exchange it for a monomial. And that's always a nice thing. What if you had a 1 plus x squared? What could you exchange that with? Well, not this, not that. This one would be a good one to match up with that one, because if you make the cotangent be x, you'd be in business. This one would also be a good one to connect with that one, because if you made the tangent x, you could turn the tangent square plus 1 into a monomial. And every time you can exchange a binomial for a monomial, you should say winner, winner, chicken dinner. It's a good thing. How about these ones over here? What do these remind you of? What sort of exchange could you use on these ones? This one tells you that if you have something like this, x squared minus 1, any variation of x squared minus 1, if you can make your substitution secant should be the x. If you can make that substitution, x equals secant theta, then in fact this whole polynomial or binomial would be exchanged for a monomial, just one thing, a tangent. And the tangent square will play much nicer with square roots, with fractions, with multiplications. It will play nicer than a secant square theta minus 1. So your trig identity sheet is full of these cases where binomials can be exchanged for monomials. And this is a brand new, much more powerful way of looking at identities. Even the double angle paragraph on the famous identity sheet. Look at this. What is this over here? This is binomial. Mondays. What is this over here? Monomial. Sunday morning by the beach. You see that? Even this one too. This one, well, you can move the 2 over, so you can say 2 sine square theta. That's equal to 1 minus cosine 2 theta. But now we're suggesting an incredibly powerful way to look at it. You look at the right side. Okay, look at the right side. What do you see there? 1 minus cosine 2 theta. Binomial. No good. What do you see on the left hand side? Monomial. Oh, beautiful. Every one of this one, you move the 2 over. It's also an exchange rate where you take a binomial and exchange it for a monomial. So is this one. So is that one. There's so many of them. Almost all of them show you a way of exchanging a monomial for a binomial. That right there will make you powerful. It will make you the life of the party. And wait, there's more. I gotta show you some more. Let me find it on my trig identities page. Right here. Bam. Every one of these, look, on the left hand side you have a sum. Something plus something. On the right hand side you've got no sum. If you've got no sum, you've got no Mondays. No Monday, one term. Often, not always, but 99% of the time, monomials are better to work where they play nicer with exponents, with roots, with everything than binomials. So this is another set of really powerful exchange rates where you're exchanging a binomial for a monomial. Oh, but I saved the best one for last. The most famous exchange rate where you exchange a binomial for a monomial Has to be. This is the most famous one in all of mathematics and all of science. The most famous equation. In fact, is one of these. It's an exchange rate where you exchange a binomial for a monomial. You guys know what it is? Couldn't have been anybody else invented it other than the master of us all, Euler. Euler did it right here. This is the most famous exchange rate where you exchange a binomial, exchange for a monomial. Oh my goodness, you could take square roots, you could do the MOV like you did in trig, you could, I can't even tell you. This is huge. But it's another one of the best examples of exchanging a binomial for a monomial. Maybe someday I'll have time to put that in the right perspective. For now though, we gotta let it slide. Come back to calculus. Where were we? These two worlds. World of binomials, world of monomials. All you have to do is become really, really good at matching it up. And I talked about that before, but I'll do it again. If you have 1 minus x squared, you want to match that up with, say, 1 minus a cosine square theta. Because then this will turn into a monomial. Look at that. It's sine square theta. I told you. Or you could also match it up with 1. This one is interchangeable. You can match it up with 1 minus sine square. If you have a plus there, you know, that's not a good matchup because 1 plus cosine doesn't turn into something famous. However, 1 plus a tangent or a cotangent, that turns into something famous. That turns into a monomial, secant square theta. What if the x was positive and the 1 was negative? Well, again, if it was cosine square minus 1, that doesn't turn into something famous per se, or at least not. Here's one that turns into something famous. You'd want to do secant square theta minus 1. That turns into something famous, a monomial tangent square theta. So as long as you can remember how these match up, these are just some examples, but I'm telling you, you got to read the identity sheet and go through them. There's tons of them that help you exchange binomials for monomials. If you get that idea, if you get your head around that idea, you become super powerful. You'll be able to do just about any of these trig ones that pop up in any trig book whatsoever. All right, talk is cheap. Let's get ready to rumble. How about 1 minus x squared? For this one, you've got to make a choice. What should your dictionary be? You got to think, should my dictionary be x equals tangent theta? Well, if it is, then you got to think 1 or 2 steps ahead. Will the 1 minus tangent square turn into something famous? And the answer is no, that's nothing famous. How about x equals 1 minus secant square theta? Well, that would be negative tangent, and then it's going to be hard to take the square root. So after a couple of these, you realize that maybe x could be a sine or a sine or a cosine. Either one will work. Because if you just think 1 or 2 moves ahead, what's going to happen? This will be 1 minus a sine square. Is that interchangeable for a monomial? And the answer is yes. That's something famous. 1 minus a sine square can be exchanged for a cosine square. Winner, winner, chicken dinner. Cosine theta, d theta. Here's my little dictionary. It's all over now. Watch me. 1 over the square root of 1 minus sine square theta. Dx can be exchanged for that, so I'll do cosine theta d theta. And what is that? That would be the integral of 1 over the square root of cosine theta d theta. No, cosine square theta times cosine theta d theta. Here, assuming this is a positive, we're going to go with a positive cosine theta d theta, cosine theta d theta. Here, sometimes you may have to be careful. If you know more about this integral, if you know the limits, there are some places where you might want to go with a negative version or the positive. It depends on the angle theta, and this becomes, because to be completely correct, this is actually equal to, if you have the square root of x squared, it's really actually equal to the absolute value of x. So just be aware, sometimes that may have to be considered when you're doing this square root of the cosine square. That will become equal to integral of d theta, and that will become theta plus a constant, and then it's customary to switch back. See if you guys can see that. Customary to switch back, so I use my dictionary. My dictionary says x sine theta is equal to x, so therefore theta is equal to sine inverse or arc sine of x plus a constant. And there you go, we did it. We found an antiderivative. Pretty easy, right? The key idea was to find a correct exchange rate here, 1 minus x squared, that would turn it into a monomial, and of course sine does it. We could have done the whole process with cosine. It would have worked just as well. And you would have gotten an equivalent answer. Might look a little different, but equivalent. All right, that was fun. Let's do another one. What if there were 9? What if they had a 9 instead of a 1? How would that change things? Well, see, none of the famous trig, none of these have a 9 in there. They all have 1s. So that presents a problem for a little bit. But if you're creative, you can get around that. You can think to yourself, you know what? I can't mess around with a 9. No matter what I substitute here for x, that won't change that 9. I could make x be 1,000 or million, 3, 9, whatever. It's not going to change the fact that there's a 9 there because there's no x's around the 9. So none of the x's will matter. So, if you can't kill it, what you have to do is you have to join it. You must put a 9 on here too so that you can factor out the 9. That's the idea. So, here's a good substitution to try. Let's try a red substitution. X equals 3 sine theta. Now let's try to think 1 or 2 moves ahead of that. What would happen when I take x squared? X squared would give me 9 sine square. I'd have 9 minus 9 sine square. And that's going to work perfectly. Because this will be the integral of 1 over the square root of 9 minus 9 sine squared theta, and I have a 3 cosine theta d theta. That's my dx. And that becomes integral of, see, I could factor out that square root of 9. 1 over the square root of 9. 1 over 1 minus sine squared theta, the square root, times, oh, I have a 3 there. That 3 comes out as well. Let me write it nicer, because that's not the kind of teacher I am. So this will become, I could take out the 3 and I take out the square root of 9, which of course is going to be 3. But I'll deal with that later. And that leaves a cosine theta d theta in here. And this will become cosine square. And I will have to take the square root. And that will cancel this cosine. And I will have 3 over 3 times the integral of d theta, which will just be integral of d theta, which will just be theta plus a constant. Which of course, right here, I gotta do a little tweaking with the dictionary. I got that x over 3 is equal to sine theta. That puts theta at arc sine of the quantity x over 3 plus a constant. And there you go. Pretty easy, huh? Only variation is if you have a 9 there, what you have to watch out for is, well, you can't kill it. You gotta join it. You gotta make a 9 in that spot right there. To make a 9, well, you know you got to square it, so you take the square root of the 9 and put it there. If had this been a 5, I would have made a square root of 5 there, so that when I square it, I get 5 and I could join it and pull it out. Capiche? Want to see another one? What about this one? This one has a plus. See that? Then cosine is not going to work because 125 plus 125 cosine, that's nothing famous. I think I got to go back to tangent on this one because I know that. The square root of 125 tangent theta. What will dx be? The square root of 125 secant square theta d theta. This will turn into, let's keep it with yellow. This will turn into 1 over the square root of 125 plus 125 tangent square theta. And the dx would be square root of 125 secant square theta d theta. And everything, I know it looks crazy, it looks complicated, but everything will turn out nicely. I'll tell you, because we're going to do something nice here. We're going to exchange this for a monomial. That's the secret of today's lecture. Square root of 125. I've got another one over there, square root of 125. And this will give me 1 over the square root of 1 plus tangent square theta secant square theta d theta. And here it is. I told you, 1 plus tangent square. What can you exchange that for? You can exchange that for, of course, a secant square. So this becomes, I'll go over here. This becomes, by the way, this is just 1. So this becomes the integral of secant square theta d theta all over square root of secant square theta. That kills one of these because secant square root will give you just secant. That will become the integral of secant theta d theta. And that's something famous, something we've done before actually. One of those fancy tricks where we multiply top and bottom by secant theta plus tangent theta. Something out of nowhere. And it turned out to be a use up. You guys could watch the video if you want. This will become, what will this become? This will become ln of secant theta plus tangent theta plus a constant. Oh, absolute value there. There you go. Well, of course it's customary to change back your thetas. So while this answer is correct, it's not customary to leave it in thetas. Be a good citizen here. Use your dictionary. Change back your thetas to x's. Okay. I'll do that right here. Actually, I will do that in another page. We shall clone this one. Let's do it here and come back to this. So let me just focus on changing, okay? Because this requires a little bit more of attention. So I'm looking at the at the statement here. This statement says that x equals square root of 125 tangent theta. Another way to write that statement is to say that tangent theta is equal to x over the square root of 125. Course, and if you've done your right angle trigonometry, that's describing a triangle with a certain ratio. It's telling you if you have a triangle with angle theta, the ratio of opposite to adjacent is x to square root of 125. And then you can use Pythagoras to figure out the other one. X squared plus square root of that will give you this 125 plus x squared. That's using Pythagoras. And now I've got all sides, and this came from nowhere. It didn't come from La La Land. It came from the dictionary, just applying the dictionary, a simple statement about ratios. And what that's used for is that's used to change back your thetas. Now I got to figure out what's secant theta and what's tangent theta. I look at the dictionary. What's secant theta? Secant theta is a ratio. A ratio is the opposite of the cosine, so it'd be hypotenuse over the adjacent, right? Hypotenuse over adjacent. So it would be the hypotenuse over the adjacent, and I'm looking at the hypotenuse. It's the square root of 125 plus x squared over square root of 125. And the tangent would be opposite over adjacent. So that helps me translate this. This would be equal to ln secant. Secant theta was the square root of 125 plus x squared all over the square root of 125. Plus tangent. Tangent was x over the square root of 125 plus a constant. There it is. As easy as it sounds, that's all you got to do. Of course, all this is just a lot of little algebra and stuff. The real key, the real brilliant idea was this right here, making a good substitution so that you could turn this binomial turn into a monomial right there. Whoops, there it is right there. The binomial 1 plus tangent squared turn into a monomial. And then all the magic happens. Everything else becomes easier. That's the theme for today. The whole thing. Turn binomials into monomials. You guys want to do that one? I don't want to do too many, but let me get started. I got some other ones that I really like. Okay, what the hell? I'll do it. All right. So for this one, I got to look at my famous sheet. I got to think, how in the world am I going to turn that right there, that crazy thing, into a monomial? So, of course, the answer is you look at the identity sheet. Where are you? Identity sheet. Come here. Identity sheet. I bet that's in the double angle paragraph right there. Aha. Here it is. We had, I talked about it at the beginning of class. The 1 minus the cotangent 2 theta can be exchanged for a 2 sine square theta. Yeah? That's the exchange rate. For 1 minus a cosine 2 theta. Right here, I just multiply both sides by 2. So, it's all over. By the way, it's almost similar as this one, except you move that one over there and this one over here. I'm telling you the same thing. Anyways, 2 sine square theta. So let's go back up here. I got my exchange rate. Now, where were you? I believe you were here. So I've got the exchange rate. This becomes 1 over 2 sine square x dx. Piece of cake. You told you the power is in exchanging This one you couldn't just flip over, but this one I can flip over because it's a monomial. Monomials play nice with fractions. Look at this. I'm going to go with 1/2 cosecant square x dx. Oh my goodness. Child's play. Now, you couldn't do that with a binomial. You can't just put it up there like this. It's a totally different ballgame, totally different world, I should say. This becomes 1/2 times cotangent, 1/2 times cotangent x negative plus a constant. That's a basic one, by the way. Third of cotangent is negative cosecant. And that's it. That was easy, huh? Let's do something more challenging. Oh my goodness, what happens here? Integral of 1 over cosine some stuff plus cosine of some other stuff. Holy macaroni. What are we going to do here? You got a plus here. Hey, wouldn't it be nice if there was no plus there? If this was just one monomial? Wouldn't it be nice if there was some bridge between this crazy world of binomials and a more pleasant world of just monomials? That would be nice, right? Where do you think we're going to look? Of course, we're going to look at the identity sheets. Which one do you think we're going to look at? Sums to products or sums to products? I think we should look at sums to products. Boom. This one tells you exactly how to exchange a sum of couple cosines. Cosine of something plus another cosine of something. You can always be exchanged for 2 times cosine of the average and cosine of the difference divided by 2. Got that? This telling you exactly, and there's a times here. The crucial thing is that there's a times here. 1 term, 2 terms. 1 term, 2 terms. You can get with this or you can get with that. That's the power of looking at it this way. So I'm going to go back to my integral here. Where were you? There gotta be a better way to do this, man. I think we were here. No. Yes. So this can be exchanged for, let me think. It can be exchanged for, let me see if I remember. 1 over, there was a 2 there, and there was a cosine, and I would have to take the average, and then I would have to take the difference divided by 2. Let me take the average. The average would be, I add them together, and then divide by 2. If I add them together, the pi's kill each other, and all I get is 2 x's, but then if I divide by 2, all I get is x. Yeah? Now I subtract them. If I subtract them together, the x's get subtracted, and I get 2 pi's, but then I divide by 2, I just get pi dx. But wait a minute, isn't cosine pi just -1? So that becomes just 1 over -2 integral of 1 over cosine x dx. Right? This is -1, which multiplied times 2 gives you -2, which can be factored through the integral. Look at us now. We took a binomial, exchanged it using the powerful idea, the secret sauce, exchanged binomials for monomials, and now binomials play really nicely with fractions. I could move that up actually. This would be 1 over -2 integral of secant x dx. It's all over now. This is one of the memorable ones. Remember, we multiply top and bottom by secant x plus tangent x. We just did that. There it is. Interesting, huh? Powerful idea. All right, maybe I got time for one more. Ooh, I got some nice ones here, though. Ooh, holy cow. Let me pause this. We're going in the trenches. All right, so this one I would say, hey, why don't we just factor 1 over x times x squared plus 1 dx, and then think about it. Hey, this piece right here looks suspicious. This has a famous translation into a monomial, right? If we just make the substitution, x equals tangent theta, then dx would be forced to be secant square theta d theta. That would make my integral, in terms of thetas, it would make my integral be the integral of 1 over tangent theta times tangent square theta plus 1, and a dx, which would be a secant square theta d theta. Now, at first that looks crazy, but of course we haven't done the marvelous part yet, which is the part where we do exchange for a monomial. This right here, which is binomial, we exchange it, and that becomes the integral of 1 over a tangent theta times a secant square theta times a secant square theta d theta. And that, of course, that becomes duck soup, piece of cake. Can't believe I get paid to do this. Kind of easy. that becomes just a tangent, 1 over tangent, which is cotangent, which is really cosine of theta all over sine theta, d theta, which then could be done using a u sub. I would make u is equal to sine theta, then du would be equal to cosine theta d theta. Then this would be equal to, I'll continue up here. That would be equal to the integral of 1 over u du, which would be equal to ln u plus a constant, which would be equal to ln sine theta plus a constant. Oh, wait a minute, now I gotta change back my thetas. I had x's. The original problem was in x's. So let me make a little triangle here. This one, should I do it in a new page? I'll just, hopefully we can get it from here. I'll make my triangle in white. This is theta. Tangent theta is equal to x over 1. So x over 1, that's opposite adjacent. This would be the square root of x squared plus 1. Stop me if I'm lying. Well, now I'm all business now, because look, I could figure out what sine is now. All I do is look at the triangle. This would be ln, what's sine? Sine would be the ratio of opposite. This is why I love right angle trigonometry. It's all about sides of ratios of triangles. It's the most powerful way to look at it in my view. I hate the unit circle view of trigonometry because it doesn't give you powerful things like this. At least not in a straightforward way. This would be the square root of x squared plus 1. And that would be plus a constant. Yeah? Easy, huh? That's why they pay me. And this is interesting because look, it originally wasn't even one of the squares, one of the degree 2 ones. It was a degree 3. But we were still able to do it. We pulled out that x and turned that one into a monomial. Yippee-ki-yay. Winner, winner, chicken dinner. Alright, let me scare you guys for a little bit. What about this crazy thing right here? A huge polynomial over here, degree 2 on the bottom. This is a standard procedure here. Whenever you've got degree 5 on the bottom, degree 2, what you want to do is you want to do long division. There's no, well, there might be other ways to do it, but this is really the best way to proceed, probably for our class. And that turns after you've see, it's almost time to stop. Let the music start. Trouble ahead. After you've done the long division, this is what you get. And you get something easier. You would get, this is x to the 4th divided by 4 plus 2x squared divided by 2 plus x minus 2. And this is still an integral that you have to contend with, 3x squared plus 5. So you've cleaned up the problem much, much easier. That piece is easy to do. That piece is easy. This is a quotient that came from the long division, and this is the remainder. And you're left with this kind of integral, which is basic, which is really a classic trig substitution. You would want to make, you can't change the 5, so you got to join it. So you'd want to make your x, be equal to square root of 5 tangent. Theta is a good one because if I had 5 tangent